While I've talked a lot about Taylor series, there is one thing that's very easily overlooked. We've talked about how if we have a function, we can write its Taylor series centered at some point A. And we've also talked about how to find the interval of convergence. However, the part that's easily overlooked is, while we know it converges, we don't know what it converges to. We still don't know that this series actually converges to the function, which is what I've been claiming. So now we want to talk about how we actually know that this series converges to the function on this interval of convergence. I've previously talked about Taylor's theorem, which says that if I have my function f, it's equal to the nth derivative Taylor polynomial centered at A plus the remainder. And during this, I am assuming that f has derivatives of all of the orders on my interval of convergence. So once again, assuming that all of my derivatives exist on my interval of convergence, the Taylor series for f centered at my point A is going to converge to f for all x in this interval of convergence I, if and only if the limit is n goes to infinity of r in x equal to 0. So I'm going to need this term r in x to go to 0 as n gets bigger, so that's saying that the Taylor polynomial and the function are getting closer and closer. So this is what I actually need. And just a reminder, this remainder is defined as the n plus 1 derivative at c over n plus 1 factorial times x minus a to the n plus 1, where c is some point between x and a. So even though we have this nice form for the remainder, it may be very difficult to show that the limit of this remainder is actually 0. But let's look at a couple of cases where it is actually possible. So I want to show that the Maclaurin series for f of x equal to e to the x converges to f for x being anywhere between negative infinity and infinity. I've previously talked about this particular series and said that the interval of convergence is negative infinity to infinity. And you can double check that yourself as well. This is definitely the interval of convergence. In this case, I have that my remainders are e to the c over n plus 1 factorial times x to the n plus 1, where c is somewhere between 0 and x. We know that e to the 0 is 1, and so we can say that e to the c is always less than or equal to e to the absolute value of x. E is increasing, so if x was negative, we're going to absolute value it and make it positive. And if it's positive, the fact that this is always increasing and c is less than x gives this to me. This then tells me that the absolute value of the remainder is e to the absolute value of x over n plus 1 factorial times the absolute value of x to the n plus 1. Taking the limit as n goes to infinity then gives me that that's e to the absolute value of x times the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 factorial. And this is equal to 0. We're using the fact that x to the n over n factorial is equal to 0 to find this. So we do have that this converges to f. And I want to show the Maclaurin series for sine of x, which is given by x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. Converges to f of x equal to sine of x for everything between negative infinity to infinity. So once again, we need to show that this remainder has a limit of 0. Just a reminder, that means the n plus first derivative of f evaluated at c over n plus 1 factorial times x to the n plus 1, where c is some number between 0 and x. Well, first it's important to note that the numerator of that, the n plus first derivative, is going to be either plus or minus sine or plus or minus cosine. But because of this, we know that sine and cosine are always trapped between negative 1 and 1. So the absolute value of the n plus first derivative of f evaluated at c is always going to be less than or equal to 1, no matter what c is. This then tells me that the absolute value of the remainder is less than or equal to the absolute value of x to the n plus 1 over n plus 1 factorial. And if I take the limit as n goes to infinity of this thing, the absolute value of x to the n plus 1 over n plus 1 factorial, we once again get 0. So the absolute value has to be less than or equal to 0, which means it has to be equal to 0. Therefore, this one will always converge to sine of x.